Test. So we're going to continue our discussion about abstract algebra, but let's see what can be done first. So what is this? What should I do here? Okay, so today we're gonna continue the discussion about abstract algebra. So last time we made an example of relation which is symmetrical and transitive but not reflexive. But the example is kind of weird because we used an empty set. So basically last time so maybe I should repeat myself first. Remember that relation on A on a set X, for example, maybe better using the letter A, is subset of A cross A, right? This relation. So actually, when we take R to be an empty set, it is an okay example because we can check it that this empty set satisfies the transitivity and the symmetric property, but not the reflexivity, the reflexiveness of empty set is not right. But actually we can take a simpler example. Let's say A equals 1, 2, 3, and we take R to be the set of collection, let's say 1, 2, 2, 1, 2, 2, 1, 1. Right. So we can check that whenever, so for example, this one is an element of R and that one is an element of R. So then according to transitivity, 1, 2 is an element of R, or 1, 2 and 2, 1 is in R, therefore 1, 1 is in R, right? So transitivity and symmetric property of R is obvious from the definition of R itself. How about the reflexivity? Is it reflexive? So we need to check again the very definition of reflexive property. It requires that for any element of A, so reflexive means that for any element in A is in relation with A, right? Meanwhile, in this relation R, 3 is not in relation with 3, so R is not reflexive. Okay, so that's the one that we discussed earlier. Oh, okay, you cannot see this part, so okay, so it's getting chopped off a little bit here. So this should be 1, 1 here. Okay, right. So the next chapter, which is about integers. So first of all, we have mathematical induction. So we will skip this. I'm assuming that you are kind of familiar with mathematical induction, but perhaps we will try to do some exercise using induction. So here, the application of the induction. First, we can prove the binomial theorem using mathematical induction, and then there is the second principle of mathematical induction, which is usually called as strong induction. Yeah, this is strong induction. Okay. And then the other thing is that so this book is using the approach that induction is more obvious than the well-ordering principle. Usually in another book they use the approach that well-ordering principle is more obvious than induction, and in that sense usually the book proof that the induction theorem holds true because of the well-ordering property of the natural number. So, but in this book, it is vice versa. So we use induction to show the principle of well-ordering, which says that every non-empty subset of the natural number is well-ordered, meaning that every non-empty subset of a natural number is having a smallest element, right? So for us, let's just take both of them, right? If you are interested in finding out the relationship between the two results, you can try showing that the two are indeed equivalent. So what I'm trying to say that this theorem and induction are equivalent. So as an exercise, you can try to prove that if we have a well-ordering, then we have induction, and if we have induction, then we have well-ordering. So that's it, right? So this book is using the approach that the induction is more obvious, then the author proves the principle of well-ordering from the principle of mathematical induction. So, and you can try the other way around. Try to prove the principle of mathematical induction by using the principle of well-ordering. Okay, so what's next here? Okay, so this is about division algorithm, which is accidentally or whatever it is asked by Wiwit Ambarswati. Okay, so this one, right? So I think I will give a little different proof. So division algorithm says that A in Z, B in Z be positive, such that then there exists a unique what did I do here? A unique Q and R such that A equals to QB plus R, where R is greater or equal to 0 and less than B. Okay, so that's the theorem. Yes, unfortunately, today we discuss this topic in English. So some other audience which is not able to speak Indonesia can participate. And also for Indonesian student, you can also try to familiarize with English, even though my English is also not so great, but well, we can learn from each other. Okay, so recall the floor function. This is the smallest or the biggest integer which is smaller than x. It is the greatest integer. Smaller than x. Okay. So if we, so basically this q is the quotient, right? So if we like performing a division, let's say for example, if we want to apply this where a is 10, for example, b is 3, right? So how do we get this q exactly? So we will say 10 is equal to 3 times 3 plus 1, right? Something like that. And we get this 3 from dividing, so this 3 in the box is exactly the floor of 10 over 3, okay? So as a candidate, we can propose that our q to be what? The floor of a over b. Okay, so this is the something that come up in our mind in order to find out the proof, right? So let q equals to the floor of a over b. We claim that using this q, then we can find the r. So then we know, according to the definition of the floor, that the floor of a over b is less or equal to a over b, right? Because this is the definition, that the floor of x is always less or equal to x, right? So now if we multiply both sides with q, okay, so I need to make sure first. Okay, I think this is a special case when okay, I think I need to make sure first that this is positive as well, right? So, well, maybe we need to fix the proof later. So apparently this proof only works for a and b to be positive numbers. So then if you so since a and b are positive, then the q is non-negative, right? So if we multiply both sides of this inequality with a non-negative number, okay, I think we need to think more about this proof later. So let's see first. Oh no, this is not I want to do. Actually, it's okay. Okay, I'm sorry. So actually I want to multiply with b, but b is positive, so this is okay. This is okay. A can be any integer, and then if I multiply this with b, this is gonna be smaller than a over b times b, which is a. So we know that a is bigger or equal to this one, right? This is equal to qb, or this, hold on, let's like this first, okay? And then, so a minus this is greater than 0. Therefore, we can take R to be this. Right? So we know at least from this that our R is greater or equal to 0. Okay. So then what we need to show is that R is less than B, and R and Q satisfies this. It's obvious satisfying this one, right? So by definition of R and Q of R, A is equal to A over B times B plus R, which is QB plus R. So then what we need to show is that our R is less than B. And we can use contradiction. Suppose on the contrary, R is greater than B, then this guy, A minus floor A over B times B, is bigger than B. So in particular, we have, this is equivalent to B, A over B plus 1 is smaller than A. So then we have the floor of A over B plus 1 is smaller than A, but this guy is clearly smaller than the floor of A over B. I'm sorry, this is A over B here. But this leads us to a contradiction. Why is that? Remember that the definition of the floor is the greatest integer which is smaller than A over B. But here we come up with a bigger integer than the floor A over B, but it is smaller than A over B. So this contradicts the definition of the floor of A over B. Okay, so at least we show the existence of Q and R, right? And we need to prove the uniqueness, but I will leave the uniqueness to with so that the result I'm not quite understand what's the question. The contradicts. Okay, so therefore, yeah, the Q and R that we take satisfy the requirement. And the uniqueness is left to read to the audience. The uniqueness is left to the reader? No, I don't know. Oops. Okay. So that's the division algorithm. Well, actually, it's not algorithm yet. That's just a division theorem, something like that. Okay, so next one is about common divisor. So when we say that, so this A, B, and K are integers, and when we have B equals A times K, then we say that A divides B, or A is a divisor of B, and we use this notation. Okay. And an integer D is called a common divisor of A and B if that number at the same time dividing A and dividing B. So it's a common factor of A and B. And we say a positive number to be the greatest common divisor if this number, first, at least it needs to divide A and B. So D divides A and D divides B, which is the same thing as saying that D is a common divisor of A and B. And moreover, if we find another common divisor of A and B, then this common divisor still needs to divide the D. So if there is D prime which divides both A and B, then this D prime divides B as well. So that's the definition of the greatest common divisor of A and B. Now this is an interesting theorem. If we have two non-zero integers A and B, the claim is that there exist integers R and S such that the GCD, so GCD is the abbreviation of greatest common divisor, which we defined earlier above. And so we say that if we look at the GCD of A and B, then we can find integers R and S, so that this GCD can be written as some kind of linear combination of A and B, right? So let's do this in our scratch paper here. So we have A, B integers, the claim. There are RS, integers RS such that the GCD of AB is equal to RA plus SB. Okay, so first we show the proof. Consider the collection of all integers in this form. So like Ka plus Lb, where K and L are integers. Okay. So the candidate, our candidate to be this Ra plus Sb. So remember that the GCD is positive. So then this Ra plus Sb should be positive as well, right? So then our candidate to be this GCD is the smallest positive element in here, right? The smallest positive element. So then we need to show that this set has the smallest positive element. So how can we make sure that such element exists in this set? So to show that it exists, let us intersect this set with the set of natural number, right? So basically this one is saying that look at all the collections of Ka plus Lb which are positive. How do we know that this set is non-empty? Let's call this as S, right? Since first of all, we need to emphasize that when we define GCD, A and B cannot be both 0, because we cannot define the GCD of 0 and 0, right? Why? Because any integer divides 0. So there is no greatest integer which divides 0, right? So this is A, B are not both 0. Okay. Now if we take the K to be A itself and the L to be B. So I need to write this in the form of A times A plus B plus B. This is A squared plus B squared. Since not both of them equal to 0, then at least A or B is non-zero. If one of them is non-zero, then the expression of A squared plus B squared is definitely positive, right? So therefore, this guy is an element of S. So we know that S is non-empty. Hence, S is non-empty. But according to the well-ordering principle, if we have a subset of the natural number, then it must be, it has to be, has the smallest element, right? So by the well-ordering, S has the smallest element. Let's call it as what? C, for example, right? And this is our candidate to be the GCD of A or B, of A and B. So how do we show that this candidate is indeed the GCD of A and B? Then we just need to verify this particular element satisfies the definition of GCD. So recall that definition of GCD, D is a GCD of A of B if first this guy, the D, need to divide A and B, and secondly, if there is another number which is a common divisor of A and B, if E, for example, divides A and divides B, in order D to be the greatest, then E have to be divides D as well. Then D divides E. Okay, so then what we need to do is just to verify that this candidate, this C, satisfy these two conditions. If C satisfies both of them, then C is the GCD of A and B. So good morning to Jordan Fitriansa. Maaf, this morning we discuss this in English, even though my English is not that great. I know, so please do not criticize me. Okay, so what? So first, let's check it out if C is really a common divisor of A and B, right? So what we know about C so far is that C is the smallest element in S. So in particular, C can be written as K times A plus L times B. So how do we prove that C divides A? Okay, so then the division algorithm comes to the rescue. So apply the division algorithm to A and C. Apply division algorithm. This is H and M to A and C. So write A as QC plus R, where our R is greater or equal to 0 but less than C. Okay. So if C is not a divisor of R, then the remainder must be greater than 0, right? since we want to show that C is indeed a divisor of A, we want to prove that R is equal to 0. So let's see what's going to happen if R is non-zero. So if R is strictly bigger than 0, then R is positive. Of course, that's the same thing as saying R bigger than 0, but nevertheless, that's okay. Positive. And R is equal to A minus QC. Let's say our C is equal to SA plus TB. Remember that C is the smallest element of S, and every element of S can be written as a linear combination of A and B. So then, if we plug in this C into our equation, we have A minus Q SA plus TB. So we have, factoring out the A, 1 minus QSA plus TB. But this is a contradiction. Can you see? Can anyone see? This contradicts to which statement? Let me have a drink first. Anyone can see why we have a contradiction? So from this, what we can say about R? So look here that R is also a linear combination of A and B. Right? Does R positive? Is R positive? Yes, it is positive. It is positive and it is a linear combination of A and B. So from this statement, we can say that then R is in S. Now if we compare R with C, which one is bigger? Let's see here. Okay. Moreover, R is smaller than C, right? But can we have such R? Recall what is again the definition of C? It is the smallest element of S. But here we can find an element of S which is smaller than the smallest element. So that it doesn't make sense, right? So then it is a contradiction, right? Contradiction to the fact that C is the smallest element in S. Then, what's wrong then? Then R cannot be positive. So R must be 0. Therefore, R equal to 0 and A is equal to Q times C. So C is a divisor of A. And by similar argument, and if you're not convinced yet, you can check it out by yourself. Similarly, by similar argument, C is a factor of B. Yeah. So at least we have verified that the first requirement to be a GCD is satisfied. In order to be a GCD, that element, that number needs to be a common factor of A and B. Now let's check the second requirement. So we need to first assume that there is another number which is a common divisor of A and B, and we need to show that this new number still divides our C, right? So okay, suppose E divides A and E divides B. Oh, this one is easy. Then E divides this guy, SA plus TB. Well, I'm kind of jumping. I'm assuming that you are familiar with division property, divisor property. So if E divides A and E divides B, then E divides a linear combination of A and B. But this is exactly C. So E divides C. So then we verified. Oh, this is wrong. I'm sorry. It should be E divides D, because we want D to be the biggest one, right? So that's what we just did. So E divides C. Okay. So we know that if we have a GCD of two numbers, then this GCD can be written as a linear combination of that two numbers. Okay, so let's go on. Let's continue. And the next one is the Euclidean algorithm. Oh, okay, now it is exactly the Euclidean algorithm. And before that, we need to emphasize that whenever two integers are relatively prime, which means that their greatest common divisor is 1, then there exists R and S such that AR plus BS is equal to 1. So usually this is widely referred as Bezout lemma. Right? So if you want to use that result, it's better to refer to it as Bezout lemma. Okay, the next one is the Euclidean algorithm. So I don't know. I think let's just prove using my way. So let's prove it. Page. The Euclidean algorithm. So first recall that if we have two integers which are not two integers, yes, A and B, then according to the division algorithm, we have A is equal to QB plus R for some Q and for some R, right? So first I need a lemma. So I claim that the GCD of AB is the same as the GCD of BR, right? And one way to prove that two integers are the same, or two positive integers are the same, we just need to show that the first divide the second one, and the second one and the second one divide the first, right? So we will prove that the GCD of AB divides the GCD of BR and vice versa. So which one is easier? So what do we know about GCD AB? Clearly GCD AB divides A, and GCD AB divides B. Hence, the GCD of AB divides A minus QB. But this A minus QB, if we move this QB to the left hand side, then we have R. So GCD AB divides R. But we know that GCD of A and B divides B as well. Hence, thus, what we can say if we have this one. According to the second property of GCD, remember that if we have another number which divides B and R, then this common divisor needs to divide their GCD. So thus, this common divisor, which is a common divisor of B and R, has to be divides the GCD of B and R. Right? And the other way around. Okay. So, and the other way around, we need to show that the GCD of B and R divides GCD and A and B. Selamat pagi juga, Wahyu. Okay, so how do we proceed with that? Okay, we can just try the same line of argument. Notice that GCD of B and R divides B, and GCD of B and R divides R. And we use this relationship that A is equal to QB plus R. Then, because of it divides B and R, then it divides QB plus R. Then GCD of BR divides A. Okay, but we also know that GCD of BR divides B. So then GCD of BR divides the GCD of AB. So we have these two statements, this one and this one. And both of them are positive numbers. So if we have two numbers which both of them are positive, and let's say the two numbers are x and y. If x divides y and y divides x, and both of them are positive, then x have to be equal to y. Therefore, okay, in conclusion, GCD of AB is equal to GCD of BR. Now this lemma is very handy in order to create an algorithm to find the GCD of two numbers. So how can we do that? We'll give an illustration. Well, it's a proof actually. So first we have A is equal, so first we apply the division algorithm to A and B. Then according to the division algorithm, there exists Q and R such that A is equal to QB plus R, right? With the requirement that our R is bigger than 0 and less than B. Next, we apply the division algorithm to B and R, right? So on the first stage, we apply the division algorithm to A and B. The next one, apply the same algorithm to B and R. So we have something like this. B is equal to, let's say Q, should I call this Q0 or Q1? Q0. R plus R0, something like that, for example, right? And then, so what is the requirement of R0? According to our division algorithm, this R0 have to be greater or equal to 0, but less than R, right? Okay. The next one, apply again the division algorithm to R and R0. Let's say R is equal to Q1 R0 plus R1. And again, the R1 need to be less than R0. Okay. So apply this several times until, so here, what we observe what? So first we have B, right? And B is bigger than R. R bigger than R0. I think I shouldn't write in this weird way. So B bigger than R. R bigger than R0. R0 bigger than R1. Okay. Since B is finite, then at most after b steps, we will reduce this remainder into 0. So at some point, this r will be equal to 0 for some n, right? Let's say it is when n plus 1 is equal to 0. So the thing is a little bit delay. What's going on here? Why I don't see what I wrote on the tablet? Okay. Okay, so that's the first time the remainder is equal to 0. So let's say this is what is the pattern here. Let me write this is if it is r0, then q2 r1 plus r2 here. So if it is rn, for example, it's gonna be qn minus 1. No, something wrong here, something off. So this has different too. So if it is rn minus 1, it's gonna be qn plus 1. This rn plus 1. And the previous step is this one, qn rn minus 1 plus rn. Okay, so let's say that the r with index n plus 1 is the first time that the remainder reaches 0, right? So according to our algorithm, our lemma above, that the GCD of, here maybe I should put like this, GCD of AB is the same as the GCD of BR. And then the GCD of this and this will be the same as the GCD of R and R0, equal to GCD of R0 and R1, and so on, right? Like that. GCD of like R, and the last time is gonna be Rn, comma Rn plus 1, right? But Rn plus 1 is equal to 0. Okay, so from this last statement, then what is the GCD of Rn and 0? Remember that any integer divides 0. So especially Rn divides 0. So then the biggest integer which divides Rn and 0 is Rn itself. Okay, so this algorithm then says that applies the division algorithm several times until you reach the remainder equal to 0. When this guy is equal to 0, then the GCD is the previous remainder. So this is gonna be the GCD of AB. So that's basically what the so there's question that if it is R is greater or equal to 0, in general it is greater or equal to 0. Yes. So, but if it is reaching 0, then we are done. The Euclidean algorithm is finished when the remainder is exactly 0. Right? So let me repeat myself again. So in order to find the GCD of two numbers, apply the division algorithm several times until we have the remainder equal to 0. Then the GCD is the previous step, the remainder of the previous step. Okay, let's try to do some example. What is this? That is okay. So here we want to find this and that. So would you like to try? 945 2415. 945 2415. GCD of 21 I forgot. 2415. $9.45 like this. Okay. So go ahead, give it a try. So let me do the first step of division algorithm, right? So 2415 is equal to, what is the biggest biggest multiple of 945, which is still smaller than 2415, which is 2, right? 2 times 945, that's gonna be 1890. So the remainder will be what? I'm not good at arithmetic. 525, I guess. Please correct me if I made a mistake. 5142. Okay. Okay. So this is the B, that's the R. And then you apply again the same algorithm to these two numbers. 9045 is what? Okay. Okay, give it a try. I need to fetch some drink. Kenapa ini bau online. Okay, so if we divide 945 by 525, that's gonna be 1, and the remainder is 420. 525, 1 again, 105, like that. Please stop me if I made any mistake. 420 is equal to 4, right? That's even. 4 times 105 plus 0. So according to our algorithm, then the GCD of these two numbers is the previous remainder. So GCD of 2415 and 945
See ya.
Is
Get back in the booth.
105. Any question about that? Let us check the result here. Where is it? Yes, that's right. Okay. Well, I think we need to stop since it's Zuhur already. Let's check out what we can learn on the next page. So prime number, Euclid, fundamental theorem. Okay, it's almost done. I think we can consider this chapter to be done, and if you want, you can do the exercise. For those of you who just joining with this lecture, you can check out that I used the book that freely available. So the title is Abstract Algebra by Thomas W. Judson from Austin State University. So if you want to tag along, please obtain a copy of this book. I think you can search by the title and by the author. Okay, so thank you very much for watching. See you again on the next video. Bye bye.